In this lesson, we want to talk about gravitational motion. Now, some of the objectives that we'll be covering in this lesson speaks to using Newton's law of universal gravitation to solve different problems. We want to explain the term gravitational field strength and at the surface of the Earth and above the Earth, so to speak. We want to be able to use the term gravitational field strength. So we want to explain it and we want to be able to use it. Okay? We want to solve problems involving circular orbits, such as satellites and so forth. We want to discuss the motion of geostationary satellites and their applications. So let's begin. Now, Newton he came up with a law which we refer to it as the law of gravitation, right? So while Newton was doing some amount of work, he was able to realize that if you have two objects that have some type of mass, right, then what you would observe is that there will be a force of attraction between the masses. So here's what the law states, and we must know this law. It states that the force of attraction between two objects is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. And with most laws, we can put it in a formula. So this formula that you're seeing right here that says F is equal to G times M1 times M2 divided by R squared, where G is what we call the universal gravity or gravitational constant, and the M represents the mass of the object, so to speak. So when Newton had came up with the whole concept of gravity, when the apple fell and hit him in his head, based on that story, right? All of what happened there was due to the whole fact of gravitational forces. So the apple has a mass, good, and because the Earth also has a mass, what happened was that the mass of the apple was attracted to the mass of the Earth, right? And so, hence, there was a force of attraction between the two, right? To look at it from a sideways view, this is what is happening. Each object here is exerting a force on each other, right? So M1 is exerting a force on M2, M2 is exerting a force on M1. Okay, so the force that M1 is exerting is the same force that F2 or M2 rather is exerting, and we just put it in that equation to say that G is equal to M1 times M2 divided by R2. It says here, it is important to note that the mass of a uniform sphere is considered to be, or is considered to act as a point mass at its center. So when calculating the gravitational force experienced by an object outside of the sphere. Now, what we're really saying here is that the distance that we're measuring, right, that the distance of separation is from the center of the object, right? Because one of the things that we should remember is that the mass of an object is centered at the center, or you can say the mass of an object is concentrated at the center of the object. So if we're considering that mass, that center of mass, so to speak, then we have to take it from where the center is of each object. So that's the distance that we are focused on, right? From the center to wherever the other object is. All right. Now let's talk about gravitational field. Now, every object, right, because it has a mass, it will have a gravitational field surrounding it. And the gravitational field, by definition, is the force that a mass exerts on another mass without touching each other. And it says here that a gravitational field is an area in which an object experiences a non-contact force, right? So I must point out this to you that gravitational field or gravitational forces are what we call non-contact forces. They are forces that experience without touching each other. Then you know that we have contact forces. Contact forces has to do with when something has to be in contact with another surface, such as frictional forces, right? Now, as it relates to this thing here, we're saying that every object will have a gravitational field, and the gravitational field is just the area or the region in which an object can experience a force, right? And from this simple definition, there's a formula that we can come up with, right? That speaks to gravitational field. Gravitational field strength in this event is defined as the force per unit mass exerted by a gravitational field on an object, right? When you hear we talk about gravity constant or acceleration due to gravity, those things, what we're really talking about is the gravitational field strength, right? And we can find that by looking at what gravitational field strength is. So I should go back and point out something. As it relates to gravitational field, gravitational fields always move towards the center of the mass. So they are moving from outwards in. So this is how they look, so to speak. That's how the gravitational field look around any particular object, right? They move inwards like this towards the center, all right? That's how the gravitational fields look around any object, so to speak, that is experiencing a non-contact force, okay? Now, from this definition that says that gravitational field strength, right, is the force experienced per unit charge, we can write that to say that G is equal to force divided by mass. Now, if that's the case, and we know that the force that we're talking about is the gravitational force is equal to G times M times big M times small m divided by R squared. We could substitute that in this equation or in this formula to get G is equal to universal gravitational constant times big M times small m divided by R squared, and then there's a m being multiplied right here. So in essence, our gravitational field strength, we'll soon talk a little bit more about this, right? But our gravitational field strength is actually equal to G times M divided by R squared. You'll see that a little bit more. Now, one of the things that I want to highlight is that the gravitational force that an object experiences is the same thing as what we call the weight of an object. So whenever we try to measure the weight of an object, we're actually measuring the gravitational field. We're actually measuring the gravitational force. And so if we know that gravitational force is equal to force divided by mass, we could simply say that gravitational force is also equal to the weight divided by the mass, right? Where we can come up with a unit for gravitational field strength as newtons per kilogram. All right? Now, whenever an object is accelerating towards the Earth's surface, good, we can consider Newton's second law, right? And if that object is moving in a free fall manner towards the Earth's surface, then our force is equal to mass times acceleration. If I can recall that the gravitational force is equal to the weight, then I can equate both things to say that the weight is equal to mass times acceleration. All right? So providing that I know that the weight is equal to mass times acceleration, and I also know that the weight from definition is equal to mass times gravity, then at free fall, what we can observe is that the gravitational constant or the gravitational field strength is equal to the acceleration that the particle or that the object is falling with, which is what we call acceleration due to gravity, right? So because we're saying that the weight of the object is equal to the force that the object has coming downwards, by equating both things, both m's would cancel out, leaving you by saying that G is equal to A. So this is how we came up with the whole concept about gravitational field strength being equal to the acceleration due to gravity. And I think we know by now that the acceleration due to gravity is 9.8 meters per second, or you could say 9.8 newtons per kilogram. All right. Now, as I was saying earlier on, that we can come up with an equation that speaks to the gravitational field strength, so to speak. Since I know that the weight of a body above the Earth's surface is equal to the gravitational field, the gravitational force rather, then by equating both things, I would get this to say that mg is equal to g times big M, where big M is the mass of the object which is causing the field, right? Right. Also, it says, yeah. So let me just restate that. So since the weight is equal to the gravitational field strength, or to the gravitational force rather, then mg is equal to g times big M times small m divided by r squared, where we can cancel out the small m, leaving us with this thing that says our gravitational field strength is equal to big G, which is your gravitational constant, right? And your gravitational constant has a value of 6.67 times 10 to the minus 11 Newton meter square per kilogram square, right? And times the mass of the object that is causing the gravitational field. So in this event, if I have an object at point X, right, and I want to know the gravitational field strength that is acting on the object, the Earth has its own gravitational field lines coming inwards like this, right? So these are the gravitational field lines that are going to cause some amount of gravitational field strength to be experienced on the object located at X. Good? So the M, this is the M, this would have been the big M that we're talking about, because this is the mass that is causing or creating the gravitational field at this point. Good? Yeah. Where r squared, we know r squared is just the distance of separation from the center to where the mass is now located, to where the next object is located. Now there's something that we must talk about here, right? We want to kind of bring across a connection between gravitational motion and circular motion. Now, when objects such as satellites orbit around masses due to their gravitational field, right, the object, let me say it again, right, as the gravitational field exerts on an object, acts as an, yeah. So whenever an object is orbiting a mass, let's take for example satellites that are orbiting the Earth, right? Those objects, what we have observed is that in order for those objects to orbit around the Earth, right, the gravitational force, that exists between both objects is going to equal to the centripetal force. Now, centripetal force is a force that is linked to when an object is orbiting or rotating in a circle, and that force is always directed towards the center, right? So once the object is rotating around the surface of another object, right, we can clearly see that it is the gravitational force that is causing a circular, a centripetal force, I should say. So the gravitational force is what is causing the centripetal force, and if that's the case, then we can equate both things to say that whatsoever my gravitational force is, my centripetal force will be the same, because as we're saying here, it is the gravitational force that is really causing a circular or causing a centripetal force at that point. Okay? Let me read what this is saying. It says, objects like satellites orbit around mass due to their gravitational field, as the gravitational force exerted on the object acts as the centripetal force, which causes a centripetal acceleration, causing them to move in a circle, right? It says here that therefore, for an orbiting object, you can equate the gravitational force and the centripetal equations together, where we know that the centripetal force is equal to the mass times the linear velocity squared divided by r, where r is just the distance of separation, or in this case, r would be the let's imagine that you have the Earth right here and you have some satellites rotating around it, right? Right? That r is the distance, or you could call it the radius of the circular path, so to speak, which we consider to coming from the center of the mass, to where the object is now rotating, right? Yes. And of course, we know that the gravitational force is equal to big G, which is your universal gravity constant, times the mass times the mass of the object that is causing a gravitational field, times small m, which is the mass of the satellite in most cases, right, divided by r squared. So if we equate both of those, these two m's would cancel out, right? And in most of this scenario here, we could use this equation to find out the speed at which the satellite must be going at, or must be spinning, or must be traveling at, so that, you know, the centripetal force is equal to the gravitational force. We're now look at a few problems pertaining to that. But let's just talk a little bit more about geostationary satellites. So these are satellites that has the same period as the Earth rotates around its axis. So these are satellites that they rotate around the Earth, right? Or what I should say, these are satellites that they complete their rotation within 24 hours, just as how the Earth completes its rotation, right? So that's what a geostationary satellite is. So imagine that if you launch a satellite at a particular location 6 p.m., right, and the Earth is 6 p.m., based on how geostationary satellites work, they would complete their rotation the same time, right, as the time that the Earth is completing its rotation. So it says now that geostationary satellites follow a specific geosynchronous orbit, meaning their orbit period is 24 hours, and they stay above the same point above the Earth. So wherever they are located, right, wherever they are launched in the first scenario, right, that is the position that they are located at right throughout their entire lifetime. Okay. Now, in some cases, we can find what is the radius, or what distance should these orbits, or I should say, what distance from the Earth's surface should these satellites orbit the Earth. It says in order to find the orbital radius of a geostationary satellite, right, we must come up with an equation. And in order for us to come up with that equation, we have to take this into account. All right. So firstly, we must understand that for these satellites to move around the Earth, right, the centripetal force must be equal to the gravitational force. Good, as we would have stated. So if that's the case, we can say Fc must be equal to Fg, which is your gravitational force. And we know that the centripetal force is the mass of the satellite times v squared divided by r, and that is equal to the universal gravity constant times the mass of the Earth times the mass of the satellite divided by r squared. There's something that we must recall from circular motion, that the linear speed can be written as r times omega. So if I were to substitute for v in that equation on that side that speaks to the centripetal force, then this is what I have. Mass of the satellite, good, times r squared times omega squared, because v is being squared, so everything there is going to be squared, divided by r is equal to g times times me times ms, right, divided by r squared. Mind you that ms can cancel out, right? So we no longer have the mass of the satellites to be considered. What we're trying to gear at is finding the orbital radius. One of these r's are going to cancel right here. Let's bring this r across the equal sign. So we have r multiplied by r squared times omega squared is equal to g times the mass of the Earth. Let's make r cubed become the subject. So r cubed is going to equal to g times m divided by omega squared. Good. So we're almost there. This r that we're considering would be the orbital radius. Now, if we can recall, omega, whenever we're considering what omega is the angular velocity. And when you think back about circular motion, angular velocity is just the time taken, or the angular displacement divided by time. When we're considering a complete orbit, right, we would generally say 2 pi radians. That is the amount of angular displacement that it takes to complete one rotation. right? Whenever we're considering a circle, divided by the total time taken to complete that rotation, that is going to be t, with a capital T, which is our time period. And because we're looking at a satellite, we said that for a geostationary satellite, the time period is 24 hours. So since that I have r cubed is equal to gm, right? Gm, I can, let me see here. Yeah, I could have just divide by the 4 pi square divided by t, right? And then now just find the square root, or the cube root rather, for both sides to make r become the subject, right? So by doing that, right, 4 pi square divided by t, cube root. So this would literally give us this thing right here. If we had put in the values, right, this is what, well, this would have been r cube. All of this is r cube. But if we were to find the cube root of this number, find the cube root of that number, then it would give us this to show that this would have been the orbital radius of the satellite. All right, let's just practice a few questions pertaining to gravitational field strength. It says find the gravitational field strength 10 kilometers above the surface of the Earth, providing that the radius of the Earth is 6.37 times 10 to the 6 meters, and that the mass of the Earth is 5.97 times 10 to the 24 kilograms. So firstly, we must recall a few things here. One thing we must recall is that the gravitational field strength is given by G times M divided by R squared. Okay? Now, G is a constant, capital G is a constant, and that value is 6.67 times 10 to the minus 11. All right, so let's just remember that. So if we go ahead right now, but firstly, if this is our object, right, and this is the object that is above the Earth's surface, now we must consider the radius of the Earth, which is r, but then the overall distance of separation is from this object to the Earth, right? So we must sum up these two distances. So r is really equal to the radius of the Earth plus the distance the object is above the Earth surface, right? So in total, this is what it is then. R is equal to 6.37 times 10 to the 6 meters plus 10 times 10 to the 3 meters, which gives us a value to say that R is 6.38 times 10 to the 6 meter squared. Meter, by the way, meter. So let's go now and put these in the calculator. I'll put this in the equation. 6.6 times 10 to the minus 11 times the mass, which is 5.97 times 10 to the 24 kilograms. Divide that by our our new R value here, which is 6.38 times 10 to the 6, all of that squared, right? Then we can now find our G values in a sense. One of the things that I always recommend is that let's put the constants together. So you can go ahead and multiply the constants here, meaning that the 6.67 times the 5.97, you would get a value of 39.8. Divide that by the square of 6.38. That would have given you 40.7. And then now, in terms of your powers, 10 to the minus 11 plus 24 is going to give you 10 to the 13. And in the denominator, you have 10 to the 12. So G is really equal to 0.977 times 10 to the 13 minus 12, which leaves us with 0.977 times 10 to the 1, which is the same thing as saying 9.77 newtons per kilogram. So that would take care of that particular question as it relates to finding the gravitational field strength. All right. Yes. So that would take care of this particular question. If we ever want to find the height at which the geostationary satellite must be positioned above the Earth's surface, we could take into consideration this equation here, right? And then you would just solve for h, make h become the subject, right? So similar to what we did just a while ago in the few previous slides, we could have found out how high above the Earth's surface, right, the satellite could have been, or should basically be positioned, so to speak, right? Now we come to a concept of what we call gravitational potential, right? Based on the definition, it says that gravitational potential at a point is the work done per unit mass when moving a small point mass from infinity to that point. It says here that the gravitational potential at infinity is equal to 0, and as the object moves from infinity to a point, energy is released, and the gravitational potential energy, so the energy is released as gravitational potential energy. This energy is reduced, therefore, gravitational potential is always negative. So, since from the definition it says that gravitational potential is the work done per unit mass, we can write that in a formula, and this would take into consideration the formula that says gravitational potential is equal to the work done to move that object per unit mass, so to speak. So if you have an object in out of space, right, or in space, and it is at infinity at first, and then you want to move it towards the Earth's surface, then you would have to consider some amount of work that is needed to be done on that object. Divide that by the mass will tell you your gravitational potential. As the object moves closer to the surface, right, what we have observed is that energy is being released, meaning that there will no longer be any potential energy in the potential energy in the mass will be then converted to another form of energy, and so we say that energy is being released. Hence, why we incorporate a minus sign in this equation. But let's consider something here. Since work from a definition standpoint is equal to the force times distance, right? We could have substitute what work is in this equation that says gravitational potential, and note the symbol for gravitational potential. It's just a circle with a line passing through it, right? So the gravitational potential is actually now the force times distance divided by the mass. Now, what is the force? The force is the gravitational force, which is G times big M times little m divided by R squared. So if we were to put everything together, we get this thing that says our gravitational potential is G times M, right, times small m, times R, which is just a distance, right, divided by R squared times M. What we can see, this M, which is the mass that of the object that is moving towards the surface, those two masses would have been cancelled out. Good. One of my R is going to cancel out, just leaving me with this thing to say that my gravitational potential is equal to minus G times M divided by R. Okay. Note this formula, right? Know how to define gravitational potential, work divided by mass, right? And then you can also learn how to derive it into this equation. Know why we have the minus sign here. The minus sign just speaks to the fact that energy is being released as the object is being moved, from infinity to some point in a gravitational field. So yeah, we could practice a simple question here. It says find the amount of energy required for a 50 kilogram mass to leave the Earth's surface, right? Or to leave the Earth's gravitational field from the Earth's surface. So seeing that we know that the radius is this amount, right? And the mass of the Earth is that, we could ultimately find the gravitational field. Let me say it. We can ultimately find the gravitational potential by using this formula, right? So this formula that we just derived that says gravitational potential is equal to minus G times M divided by R. I can find the gravitational potential, but this gravitational potential is equal to the work divided by the mass. Now, whatsoever work here in this equation, this is the work, or this is the amount of energy that will be required to move the object outside of the Earth's gravitational field. So we could transpose the equation to make work become the subject. So work is equal to the gravitational field times the mass. So all we just need to do now, and we're going to forget about the minus sign, right? If we forget about the minus sign, my gravitational potential is this value here, negative 6.25 times 10 to the 7 joules per kilogram, right? Having that value, as a matter of fact, it's not joules, it's kilograms. Not kilograms, I should say. It's newtons per kilogram, right? So having said that, and manipulating my equation that says gravitational potential times the mass is equal to the work, right? Forgetting about the minus sign in that case showed us that energy was being released from the initial stage, but because the object in this case is moving from the Earth to or moving from the Earth's surface outside of the Earth's surface, in that case the object is going to gain potential energy. So rather than having a minus sign, you'd have a plus sign. So the overall energy, right, is going to be 3.13 times 10 to the 9 joules, right? All you're simply doing is taking the gravitational potential, multiplying it by the mass of the object, and that will now determine the amount of energy that is really required to move this amount of mass, right, to a certain point in the gravitational field. Okay. Here's another question that you can try. All right. So this is how much work is done by a gravitational field in moving a mass m of 2 kilograms from infinity to a point, right, that is zero point 0.4 meters from a mass m of 30 kilometers. So see if you can determine that, right? And we can talk about that some more. This question now, similar question, right? So it says to us that the Earth has a mass of that amount and has a radius. It says find the change in the potential, the gravitational potential energy, right, of a meteorite of mass m, 150 kilograms as it moves from infinity from an infinite distance rather to the Earth's surface. The meteorite starts from rest. With what speed does it strike the Earth? Good. So we can find the work that the object has, or we can find the potential energy that the object has by considering the whole aspect of gravitational potential. So if we start out with this equation, right, that says gravitational potential is equal to minus g times m divided by r, we could have clearly seen that that gives us a value of negative 6.2 times 10 to the 7. I think it's joules per kilogram. I'll have to go back and check this if it's joules per kilogram. But either way, so yeah, I think it's joules per kilogram because you're dividing work by mass. So it's joules per kilogram. Yes. So if I want to find the work, that work is the actual potential energy that the system has lost. Good. So in that event, this is the amount the amount of potential energy that the object would have lost as it moved from one point to the next, right? It would have lost about 9.4 times 10 to the 9 joules of energy. Now, mind you, they want us to find the speed at which the meteorite collides with the Earth, right? Now, one of the things that we're going to learn in subsequent lessons, right, is that once you're losing potential energy, then that potential energy is being converted to kinetic energy, right? So this potential energy that is being lost, right, is equal to a gain in kinetic energy. And if that's the case, whatsoever I'm losing, it is going to equal to the amount of kinetic energy that the system is gaining. All right. So change in potential energy is equal to change in kinetic energy. And for that reason, I could have equated these values here to ultimately find what my speed is of the object. So you can try it for yourself, right? And let's see what answers you're coming up with. You should be getting something like of this nature, okay? Yeah, you should be getting something of that nature, all right? So that's where we're going to stop for this lesson.